our third and last talk here, last but not least, of course, is Alexander Gribenko. He's a research professor at the University of Utah and a leading scientist at the Consortium for Electromagnetic Modeling and Inversion at the university. It's known as the SEMI Consortium. He also works part-time for a TechnoImaging company, which is located in Salt Lake City, that does geophysical interpretation work. His talk today is on 3D inversion of the long-period EarthScope MT data over the Great Basin area.
Good afternoon, everyone. So the title of the talk is on the screen, and we shift in the topics a little bit. So it's mostly a methodology paper, of the case studies which we will see in the morning, and at the end of it, I will show an example of real data inversion on a very large scale. So the work been done by my colleagues from TechnoImaging, Michael Zhdanov and Masashi Endo, and our friend and colleague from Barrick, Howe. Here's the outline. I will start with introduction and I'll tell you a little bit why we want to have a new development in MT inversion and what's been done in the field before, and then we will look at principles of MT inversion with distortion matrix. This is our new development complex distortion matrix. A little bit of theory there. Hope to go through with it pretty fast. Then we will look at the implementation nodes, the code which we developed, what are the features of this inversion code. And to test the code, I will show you the results of this very noisy and very distorted MT data computed from this Dublin Secret Model #2. And finally, we will look at the inversion result of the original low-frequency MT data collected as a part of EarthScope project. And I will conclude on that. So one big problem with MT interpretation is the near-surface homogeneities. They provide what's been known for quite a while, this DC shift. DC shift is the simplest manifestation of the effect of near-surface inhomogeneities. In 3 dimensions, however, the effect is much more complicated, and besides this shifting of the MT apparent resistivity or amplitude, we can also have phase mixing, and well, the data can be very distorted and very hard to fit unless you discretize the subsurface very finely. So the standard approach to address this, to be able to fit the data with high accuracy, is to have a very fine discretization of the near surface. And of course, you will need a very large machine to do that, or a cluster, to spend a lot of time doing that. What we do, besides inverting for the conductivity distribution of the subsurface, we also invert for what is known as distortion matrix. And in this way, we are able to fit the data, and we can get a much better result and assess and get the features of the geological with high accuracy. So we will present the result at the end, as I mentioned, of this original MT data set over the Great Basin area. And we found the apparent correlation between the connectivity signatures deep in the crust and some tectonic provinces, as well as metallogenic trends found in the basin. So let's look at the principles of our MT inversion, our new method. So the MT data, as we all know, is the MT impedance. We have 4 components of the MT impedance. So this is our observed data. We have 4 components of the MT impedance. And the undisturbed, if we didn't have any near-surface conductivity anomalies, this would be our undisturbed MT impedance. And this one we can fit pretty easily. We don't need to discretize near-surface too finely. But always we have some small inhomogeneities in the near surface, so those can be accounted for, and it's been shown in several publications, by introducing this distortion matrix. It can be real, can be complex, it has 4 components, so our observed MT impedance is actually a product of this distortion matrix, and this undisturbed tensor, which we will observe that there is no heterogeneity. And so our forward equation then is, this is our data, our impedance. Then we have the distortion matrix multiplied by undisturbed impedances. And so here we write it in operator notations. Again, we have the distortion matrix, and then we have forward operator A acting on the conductivity distribution. And this forward operator A is based on mobility-moving transformations or impedances. And also to get the fields, we use integral equation method to compute predicted fields before we transform them into impedances. The inverse problem, we apply standard approach of Tikhonov regularization. So we're trying to find such conductivity distribution which would minimize the difference between observed data and the data computed for this conductivity distribution. And this would be the first term. This is what's called parametric functional. So the first term of this is basically the difference between our observed and predicted data, or the norm of this difference. And the second term is the regularization term, and this makes sure that we do not feed noise and that we actually have a solution, and we can also incorporate some a priori information into this regularization term. And this is just data weights, this is the residual, the difference, data weights. We have predicted data, and this is observed data. And the stabilizing term is written out here. We have actually two parts of the stabilizer because we're working for two different properties. The first property is conductivity, and the second property is this distortion matrix. And for the conductivity, we use the first order finite difference, so we use smoothness operator. We're looking for models with smooth boundaries. And for the distortion, we just basically trying to find the distortion matrix as close as possible to undistorted data. So the C0, meaning just an identity matrix, which represents the case of no distortion. To minimize the parametric functional, we use steepest descent method, preconditioned steepest descent method. Oh, I should change it. It's actually conjugate gradient, preconditioned conjugate gradient method. And again, preconditioner is written here, but this is just something we use to accelerate the convergence of the method. And F is Fisher derivative. We use it in the preconditioner, and also we need it when we solve the minimization problem. This is Fisher derivative. We can call it sensitivity or Jacobian matrix. We have compute. This is one of the hardest part of the whole inversion, and the most time-consuming and memory-consuming parts is this Fisher derivative matrix, and we use this quasi-Born approximation to compute this Fisher derivative. To compute for with respect to conductivities, with respect to distortion components, it can be computed analytically. And some more implementation notes of the code. We run inversion for logarithm of conductivity, so we don't get any negative conductivities, and we can impose boundaries on our conductivities. And before we do the 3D inversion, we just take all of the data and we average it, and we compute the averaged sounding curve of MT, and we run 1D inversion of that average curve, and this is our initial model for the 3D inversion. We could start with a half space, but this is a lot faster. We start with pretty low speeds at this point. And to save memory and time, we only compute Fisher derivatives within sensitivity domain for each station and for each frequency. This is based on the skin depth for each frequency, so right now I think I computed to 3 times the skin depth for each frequency, because the domain is the radius is 3 times the skin depth. When we stop when our RMS reaches 1 or stops decreasing, and we run this in MATLAB with parallel computing toolbox, and we use this parallelized 3D modeling code developed in SEMI. It's called Py3D, and it's integral equation 3D modeling code. Okay, and this is it for the theoretical part. So we developed the method, and first thing we did, we tested it on this Dublin Secret Model, and this model was used in this MT inversion workshop held in Dublin, hence Dublin Secret Model. And It's, well, we knew the model beforehand. The people who invented it didn't know it, so we had an advantage, but still I think we did a pretty good job, which we'll see later. But anyways, the data set was highly distorted, so there was a lot of distortion applied to the data, and also quite a bit of noise. 5% is 5% is relatively high noise level. So pretty challenging, and here is the model. There was a full impedance data, 30 periods, then 124 stations. And here is the discretization. I'm showing what the cell sizes are used for the inversion. The model is 3 layers, actually 4 layers. There is a thin 50 ohm layer on top. The top layer has a conductor and a resistor here, so 1 ohm, 100 ohm. And this is a vertical section, obviously, and this is a horizontal section of the first layer. These are the RMS values per station. So red meaning high RMS and blue is low RMS. And on the left we're seeing the result of conductivity only inversion. So I did not include any distortions in the inversion. And the inversion couldn't converge to a reasonable level of misfit. The RMS is 6.7, which is very high. And if I run conductivity and distortion inversion, I was able to reach RMS of 1.4. So this is much better, and obviously distortion helps to feed the data with high accuracy. And these are the sections of the true model, and the model on the left we're seeing the sections of the true model. This will be vertical, these are horizontal sections at different depths. And the middle column is conductivity on the inversion. And we see that the inversion did a pretty reasonable job of recovering this conductor and this resistor here. But when we look at the shallow section, we see that those features are popping up, and the inversion tries to fit the distortion which was introduced in the data, well, unsuccessfully. Perhaps I didn't have fine enough discretization here to do that, 2 by 2 kilometer cells. And when we look at the conductivity plus distortion inversion, we have a very reasonable and quite accurate representation of the true model. And on this side, we're seeing the result of 1D inversion. As I mentioned before, running 3D inversion, we have 1D inversion on an averaged sounding curve. So here's the 1D model, depths and resistivity here. And this is the average data. So we have average apparent resistivity in phase, absorbed circles, predicted lines. And this is the final predicted data for one of the stations. We're seeing sounding curves for principal impedances, XY and YX. And the red is our observed data. You can see it's quite noisy, apparent resistivity phase. You can see very noisy data here, and you can actually see this difference. The blue curve is the predicted data by this conductivity only inversion, and the green line is the data, predicted data obtained by this inversion. And you can clearly see this static shift between the blue and green curve, and this is the effect of near surface inhomogeneity. That's what happens. The apparent resistivity curve shifts mostly apparent resistivity. There is also an effect in the phase, but it's much more subtle. So we're doing a much better job with our conductivity plus distortion inversion. These are the distortion components, this distortion matrix which I was talking about. We have 4 components of the distortion matrix, and we invert for complex distortion, and so we have real part and imaginary part, and there is no imaginary part because it wasn't introduced in the data, so we will not recover it, which is good. We will not recover something which wasn't in the data. And these are again by stations, different values of shifts, distortions. This will conclude our theoretical and model part, and we will look now at the results of the Great Basin data inversion. And as I mentioned, it was collected as a part of this NSF-funded EarthScope project. There are stations covering a large part of the US. Now there is data, the whole northwestern part. There is data now in the eastern part of the US. And So yeah, there's a lot of data which can be used for, hopefully maybe even for exploration. We use normally 98 sites out of however many there are, and the sites are approximately 80 kilometers apart. The area is very large. We used 1,000 by 500 kilometers, and six parts of 6 states are covered by this region. We work on the full impedance tensor, we do not involve deepers in this case. And these are the original frequencies, original periods which the data was provided on. We interpolated them into some regular spaced frequencies, from 24 to 23 parallel code. We assume flat surface, and I forgot to mention that this distortion can also account for topography, because topography anomalies, small topography anomalies can be considered as conductivity perturbations, as conductivity, near surface conductivity perturbation. Of course, it depends on the size and the scale of your inversion. So we are hoping that by introducing those distortions, we can get away with flat surface, and it's like we did get away with the flat surface inversion here. So here's the size of my inversion domain. So the horizontal cell sizes are 10 by 10 kilometers, and they have 48 vertical layers. They are changing logarithmically from 1 kilometer to 20 kilometer depth. This is just the slide showing you the whole picture, most of the whole picture of the inversion result, and we'll go into a little bit more details later. But here you see the state boundaries, and these are horizontal sections at different depths shown here, and these are vertical sections at different latitude degrees. And red conductive, blue resistive. There are some prominent features we can see here. There's a conductive trend here going right along the Masashi fault, and big conductors here corresponding to some geothermal areas and other things. Yeah, I didn't go deep into interpretation, but geologists. But this is the result we have, and we're going down really deep to, well, I'm running the domain running up to 400 kilometers, but we probably don't have much sensitivity below 200 kilometers because of this highly conductive Great Basin shallow layer here. The signal just drops down pretty fast inside those conductors. And so then we will compare our result with some tectonic features, and this is done to validate the inversion results, see if we can see these prominent tectonic features in our inversion. And if that is the case, then we can go ahead and look at some metallogenic trends and see if we can find any correlation between our conductivity distribution and the metallogenic trends found in the Great Basin. So this is the picture from this paper by Dickinson on the history of the Great Basin tectonics, and there are some features shown here, such as Snake River Plain. We see the boundary between Great Basin and Colorado Plateau, and well, a lot more things in this picture, but this is mainly what we see in our inversion result. And so this is a 10 kilometer depth slice of our inversion result. And the Snake River Plain, these boundaries are taken from the previous picture, which I showed you, the black and white, and digitized. And we can see that there is a nice correlation. There is this conductor which corresponds pretty well to the boundaries of the Snake River Plain. Actually, now I loaded more data to the north, and it continues to be very well defined as our conductivity distribution. And this is the boundary between Colorado Plateau and Great Basin, and we see again a nice boundary, the conductivity boundary right here, the conductive from the Great Basin side, and there is a resistive fiber on the eastern side. And also there is this resistor which we recover in the northwestern Nevada, which corresponds to what is found in Alton. So by doing this, we think we can see some prominent features, tectonic features, so the result seems to make sense, and we will go ahead and look at the metallogenic trends next. This slide, the stars, this is a 30 kilometer slice now, and the stars show large gold deposits, and only those which are larger than 2 million ounce, I think, are plotted on this side, on this slide. And we also draw here the trends, the Caroline trend and the Roberts and Eureka trend. And also there is the arc and the Bingham Comstock found here. And the main feature which we find here is that well, first there is this conductive feature which has the same alignment as the trends, as these trends, and also the mines, the discoveries are all, well, most of them are found on the edges between conductive and resistive boundaries within the crust. This is 30 kilometer slice. And we can see the same for the Comstock, we can see the same for the Bingham, and the Elite arc is showing up in the south. So we can look into this a little more. And this is a vertical section of the same result, and the top here shows the same picture we saw before, except no previous section. So here are the trends. And this red line represents the vertical section which is shown here below. And it looks like, again, we can see that this DV trend appears on the edge of this crustal conductor, so as the carbon trend also appears on the edge of this crustal conductor. This is it for the presentation. We have developed the MT8 inversion code, and we successfully applied it and tested it with Dublin Secret Model. And our connectivity anomalies, which were recovered from inverting the Great Basin data, agreed well with known tectonic features, and we were also able to correlate our connectivity distributions with metallogenic trends of the Great Basin. And we'd like to thank Virginia Mary's Consortium for electromagnetic modeling and inversion, TechnoImaging and Barrick Gold, and NSF for providing this EarthScope data. Thank you for your attention.
Okay, there's a few minutes before lunch. Questions for Alex?
Nice talk. I know at the beginning there was a lot of mathematics, but I actually appreciate the fact that when you read it, you actually took the time to explain what the terms meant and what they meant. So I appreciate that. We don't often get that. We're not all mathematics. It's nice for you. My question to you is, in the Great Basin data, you showed so the paper is essentially, you started out with how you use this distortion. You're trying to correct for the distortions now. At the end, was the Great Basin data set that you showed, was it, and you didn't show, like, was distortion a particular problem with that data set?
Well, yes, I ran inversion without distortion. I couldn't get as good of a freedom. I had a lot of noise on the near surface, and sometimes this noise will extend down to the deeper parts. And my cells were 10 by 10 kilometers. And so obviously I can't recover the near surface anomalies with this discretization. And the inversion still tries to recover them because the highest misfits are caused by those anomalies. And before it can do it, it cannot recover the deeper stuff at the bottom, which causes a lot less difference in the data. So that's the problem.
I think it would have been helpful for us. I think you would have nailed it if you'd shown the comparison between the two. I mean, that's a nice result that you got. I mean, you made it look like simple when in fact it probably wasn't that simple. So Well, I mean, the end result.
Well, the reason I included a lot of math was last time when I did a presentation, I showed liquidations, people started screaming, somebody had a seizure in the back, so. I had to go.
Do you have another question?
I was just curious, do you think you're seeing any influence from the craton boundaries and super zones?
I would probably do, but like I said, I didn't do very much interpretation on this data, presented the result and looked very briefly. There is a Brendan who might have a little more insight on that.
Behind the model, so east, you see the larger craton. And there, just
You still not here?
one of the depth loss in Grade 3, it's probably something that introduced to, well, it's just in the border below.
Does the Trans-Hudson line up with that?
So,
Does the Trans-Hudson line up with the
I'm not familiar with
So we need to do a better job. The geologist will interpret. Okay.
Thank you very much.